It's all I wanna do.
Rotational motion is an important part of everyday life. The rotation of the Earth creates the cycle of day and night, and the rotation of wheels enables easy vehicular motion. Modern technology depends on circular motion in a variety of contexts, from tiny gears on a Swiss watch to the operation of generators and power plants. The concepts of angular speed, angular acceleration, and centripetal acceleration are central to understanding the motions of a diverse range of phenomena, from a car moving around a circular racetrack to clusters of galaxies orbiting a common center. In order to understand rotational motion, it is crucial to understand the concept of radians. First, we need to start with a unit circle. Now, consider an arc length equal to 1 radius. The measure of the angle subtending 1 arc length is equal to 1 radian. If we double the arc length, so it's now the length of 2 radii, the angle is now 2 radians. From this, we get the equation theta equals s over r, where the angle equals the arc length divided by the radius. We already know how to manipulate and use variables, d for displacement, v for velocity, and a for acceleration. However, now that we are dealing with rotation, we will use the variables delta theta for angular displacement, omega for angular velocity, and alpha for angular acceleration. Under constant acceleration, the equations we used from kinematics remain the same. However, the variables are now swapped to account for rotation. Now that we understand the concept of radians and the relationship between the angle, arc length, and radius of a circle, we can relate linear and angular quantities with 2 easy equations. Tangential velocity equals radius times angular velocity, and tangential acceleration equals radius times angular acceleration.
Imagine you've got a tennis ball attached to a piece of string, and you start swinging it in circles. Whoa now, watch out for your buddy. Let's take a closer look at the fascinating physics of this simple action. You've probably heard of Newton's second law of motion as it relates to objects moving in a straight line. Turns out, Newton's second law also tells us about the net force on an object as it moves in a circle. When an object moves in a circle, its velocity changes direction. Since the velocity is changing, that means we have an acceleration. And we know from Newton's second law that if we have an acceleration, we have a net force. Now back to our spinning ball. For objects undergoing circular motion, the net force on the object is called the centripetal force. It's a weird-sounding word, but it's Latin for the phrase center seeking. It's named centripetal because the centripetal force always points to the center of the circle. The ball has a tangential velocity, so if you suddenly cut the string, it would fly off in whatever the tangential direction was at the moment you made the cut. But assuming you don't cut the string and you keep swinging the ball's tangential velocity is constantly changing directions. This means the ball is accelerating, and the reason it's accelerating is due to the centripetal force. The centripetal force acting on the ball is constantly directing the ball towards the center of the circle, your hand. This, combined with the ball's velocity, keeps the ball swinging in a circle. The same centripetal force that keeps the tennis ball swinging in a circle also keeps roller coasters on the track as they go through a loop-de-loop. So the next time you're having a blast on a roller coaster, you can thank the centripetal force.
Centripetal force! Centripetal force! Woo!
For those of you who didn't know, Boston decided he didn't have enough excitement in his life last weekend, so he decided to take his Yaris to some narrow country roads and test its limits. As he went around each turn, a centripetal force kept him from flying off the track. In this case, the force was friction. Since mass cancels, we can say that the centripetal acceleration equals the acceleration due to friction. V squared over r equals mu g. So as Bastian zipped around each turn, he was able to calculate the max velocity he could achieve without suffering a painful death.
The Earth and the Moon have existed for approximately 4.5 billion years, and during that time, the Moon has been orbiting the Earth in a choreographed circular dance. What is not so evident is that the Earth and the Moon are in a violent game of tug-of-war, each aggressively pulling on each other. The Moon's pull is evident in the rise and fall of tides in Earth's oceans. But what dictates this relationship? Sir Isaac Newton mathematically modeled this relationship and is referred to as Newton's universal law of gravitation. Newton's universal law of gravitation states that the force of gravity between two objects is equal to the universal gravitational constant times the mass of each object, all divided by the square of the distance between the two objects. G represents the universal gravitational constant. M1 and M2 are the masses of the two objects. R is the straight line distance between the centers of the two objects. The gravitational force is proportional to the product of their masses. So as the product increases, so does the gravitational force. Likewise, as the product decreases, so does the gravitational force. The force is inversely proportional to the square of the distance. Thus, as the distance increases, the gravitational force decreases, and vice versa.
The chapter concludes with Kepler's 3 laws of planetary motion. Kepler's first law states that the orbit of a planet is an ellipse with the Sun as one of the two foci. The second law states that a line segment joining a planet and the Sun sweeps out equal areas during equal intervals of time. This means that each of the shaded regions shown is exactly the same area. As the planet moves closer to the Sun, it speeds up. As it moves away, it slows down. The third law states that the square of the orbital period of the planet is proportional to the cube of the average distance from the Sun, as written in our book, Cap T squared over R cubed.